Hi everyone! In our last two videos, we talk about how to solve recurrence relation using iteration techniques, and we also introduced the techniques works for linear homogeneous recurrence relation. So today, the explicit formula will be given. So what we need to do is we want to show this is actually the explicit formula for the recurrence relation, and we show it by mathematical induction. Okay, so let's go through the examples. First examples. Suppose P of X is a recursive formula. Can we find a closed form solution? Sometimes people call the explicit formula be the closed form solution. Okay, so consider P of n equals, so P, when n equals 1, P1 is 2, and when n is greater than 1, Pn is 2n plus P of n minus 1. Okay, so what would an explicit formula be? Okay, so what is the sequence? We have the first number, okay. First term is 2, and then the second term we have 2 times 2 plus 2, which is 6. Next, we have 2 times 3 plus previous number 6, we get 12. And then we continue, we get 20. Okay, so how to get an explicit formula? We can realize A1 is 2. 2 is like 1 times 2. A2 is 6. 6 is like 2 times 3. And A3 is 12. 12 is like 3 times 4. And A4 is 20. 20 is like 4 times 5. Now, can you find the pattern? Do you see that AN is, you see A4 is 4 times 5, then AN is n times n plus 1. Okay, we kind of guess from the pattern the explicit formula should look like this. But how do we actually prove it? Okay, we can use math induction. We learned math induction in session 2.4. If you have no idea, you completely forget everything about that, please go back and watch the videos for session 2.4. Okay? Let's look at the next example. Hn equals, if n is 1, then the first term is 1. If n is greater than 1, then we have hn equals hn minus 1 plus 6n minus 6. You can see this example and the previous examples there, they are not linear, they're not homogeneous. Okay, so we cannot use the techniques of the homogeneous linear recurrence relation. Alright, let's find the first 6 terms. So h1 equals 1, h2 is the previous term plus 6 times 2, which is 12 minus 6. Well, that is 7. h3 is previous term 7 plus 6 times 3 minus 6. Well, that's 12 plus 7, so 19. And then next we have h4. h4 is 19, then plus 6 times 4 minus 6. So that's like 6 times 3, 18. 18 plus 19 is 37. Okay, 6 terms, almost there. 5 terms, 37 plus 6 times 5 minus 6, so 6 times 4. Well, that's 24 plus 37, is it 61? Okay, h6 is 61 plus 6 times 5, right? So that's 30, okay, 91. Okay, alright, can we guess an explicit formula? Okay, so let's look at the difference. Or we have 1, 7, 19, 37, 61, 91. What's the difference? Here we have 6. Here the difference is 12. Here the difference is 18. Here the difference is 24. You can see it's like a copies of 6, right? And actually, the formula, the explicit formula is Fn equals, oh sorry, I should use H. So consider this function Fn equals 3n squared minus 3n plus 1. Is Fn equals Hn for all n greater equals 1? Okay, let's plug in some number. F1. 3 minus 3 plus 1 is 1. F2. 3 times 2 squared is 4. 3 times 2 is 6 plus 1. So 12 minus 6, 6 plus 1 is 7. So it looks like it works for F1 and F2. But is it really true that this is the explicit formula? How can we prove it? Wow, let's use math induction. So we call what is math induction? First, we want to assume that Rn is the recurrence formula and Fn is the explicit formula, and we want to show we want to show Fn is really the explicit formula for this recursive formula. Okay, so let's see here. Okay. Alright, so we want to show Rn equals Fn. Okay, so first, we want to show that it is true for the base case, so R1 equals F1. Second, we want to assume this equation is true for k minus 1, for any arbitrary k greater than 1. And then we can use by induction, we can use the assumption we want to show that the statement Rk equals Fk. And then once we show that, then we can conclude that Fn is the explicit formula for our recursive formula. Okay? Alright, let's continue. Okay, so how do we show it in this case? We want to show Fn equals Hn for all n greater equals 1. Right? So let's look at the base case. Okay, that is when n equals 1, F1, well, Fn is 3n squared minus 3n plus 1. When we plug in 1, we get 1. Oh, that's H1. So, good. Check. So, second, we have the inductive case. Remember, we assume for any k greater than 1, let's assume Fk minus 1 equals Hk minus 1. Okay, so that equals 3k minus 1 squared minus 3k minus 1 plus 1. Okay, so, and we want to show, that Fk equals Hk. This is our goal. Okay. So, what is Fk? Well, Fk is replace n by k, so that's 3k squared minus 3k plus 1. And then we want to, so this kind of proof is really like you have two islands. Okay, so we have Fk right here, and then we have our goal Hk, and we want to build some bridges. Okay, it's like you're here, your girlfriend is here, You want to build some bridges so you can meet your girlfriend. Okay, so we want to build a bridge between different islands. So one way is we start with FK, we want to show and we want to arrive HK, or we can also start with HK and then we want to show that it changed until we get the formula that looks like FK, or we can start both direction and meet in the middle. Okay, so let's see what is HK. Well, HK, according to our recursive formula, what information do we have? We have HK equals HK minus 1 plus 6K minus 6. Okay. HK minus 1 plus 6K minus 6. Okay, so this is the recursive formula. And then we know HK. So HK is 3K minus 1 squared minus 3K minus 1 plus 1 plus 6K minus 6. Okay, let me highlight the hypothesis, right? So our hypothesis is here and here. Okay, so this is the hypothesis. Let's continue. Okay, so let's distribute everything. So this is k squared minus 2k plus 1. So don't forget the minus 2k. I hope you are familiar with the algebra formula. And then next we distribute, so 3k, but minus become plus 3, and then plus 1 plus 6k minus 6. Okay, let's continue distribute. 3k squared minus 3 times 2, 6k. 3 times 1, 3, minus 3k plus 3 plus 1 plus 6k minus 6. Okay, can we cancel something? What can we cancel? 6k we can cancel, right? And then let's see. We have 3 and minus 6, they cancel, right? So at the end we get 3k squared minus 3k plus 1. Oh, this is f of k. Yay! We have shown that fk equals hk. So we can say bye. Oh, I ran out of space again. I hope you still have a little space. By induction, we can see Fn equals Hn for all n greater equals 1. Okay, so Fn is in fact the explicit formula for the recursive formula. So far, so good, everybody. So this is math induction. So keep this in mind. Let's do more examples. So I hope you can pause the video and use this chance to work on the problems first. And after you're done, you can continue to play the video and check your answers with me. Are you done? Yes? Good. Let's check. First, let's look at the base case. Well, the base case is when n equals 1. Ooh, this is actually our first example. Do you remember? So f1 equals 1 times 2, which is 2. Ooh, this is p of 1, right? So good. We have that check. Second, inductive case. Assume for any k greater than 1, f of k minus 1 equals p of k minus 1. Well, what is f of k minus 1? Well, that's k minus 1 times k, right? We plug in this formula, we plug in n equals k minus 1, and we get that. And then we want to show that f of k equals p of k. So f of k, we place n by k. So we have k and k plus 1. Okay, and let's go to the other side. What is pk? What's pk by the recurrence relation? That's pk minus 1 plus 2k, right? We're using this formula and we plug in n equals k. Oh, now do you see pk minus 1? Well, pk minus 1 equals k minus 1 times k. And we also have the 2k. So here, let me highlight the inductive hypothesis, right? Oops. Okay, this guy equals this guy. Okay, let's continue. So distribute k squared minus k plus 2k. Well, that's k squared plus k. Right? Ooh, we can factor out k and then we have k plus 1. Ooh, it match. That equals fk. Then we're done. We say by induction. Okay, by induction, we have hk equals fk for all n greater or equals 1. So far, so good, everybody? Okay, so see, sometimes we find the pattern and we conjecture some explicit formula, but to rigorously show it, we can use math induction. Okay? Let's continue. Last example of this session, finally. Okay, so we want to show this Cn equals Fn, Fn equals 2 to the n. So we start with base case. So base case is when n equals, ooh, see, n is not start with 1, it starts with 0. Okay, so f of 0 equals 2 to the 0 is 1. Oh, and that is c of 0. Good. We have the base case check. And then for the inductive case, what do we do? It's actually the same step, right? We assume for any k greater than 1, we assume f of k minus 1 equals c of k minus 1. But f of k minus 1 is 2 to the k minus 1, right? Look at the formula of f. Replace n by k minus 1. And what do we want to show? We want to show f of k equals h of k. So f of k is 2 to the k, h of k. Okay, oops, sorry. Why did I use h? I should use c because in this example, we're dealing with cn, right? So ck is, use the recursive formula, is c sub k minus 1 times 2. And then c of k minus 1, ooh, that's the inductive hypothesis, right? This is 2 to the k minus 1, and then times 2. Oh, this is 2 to the k. See? They are the same. Now, so we say by induction, not hn. Why do I want to say h all the time? Because we work with a lot of examples of h, right? So cn equals fn for all n greater or equals 1. No, it actually starts with 0 in this problem. So sometimes we have to be careful. Okay, so start with 0 in this example. Okay, so look for the number. Where does it start with? So it could start with any numbers. It could start with 2, start with 3, or 5. Okay, and I also realized last example I should use p instead of h. Okay, sorry. All right, so far so good. So interesting. Oh, I have my title here as well. Okay, so in this video, we have shown how to, after we conjecture a explicit formula, we can use mathematical induction to actually prove the formula, the explicit formula we find is indeed the explicit formula for the given recurrence relation. Okay, and that's it for session 7.2, and now we have finished chapter 7. If you have any questions, feel free to ask me in class or office hours or email. Have a nice day. Bye.